All right, guys. So I am going to go ahead and get started. Um, my name is Michael Martin, as you can see on my screen. I'm going to be your instructor for Nuclear Medicine 4303. This is physics and instrumentation. And I'm excited to be here. I I love teaching and I love nuclear medicine. Nuclear medicine is an awesome profession. Um, I have had a lot of different jobs as I've gone through my life, and this is one that I love because I don't wake up in the morning thinking, "Oh, I got to go to work. This sucks." Don't get me wrong. I love being home, of course, but if you're going to have a job, it's awesome to have one that is just really cool, has so many interesting things in it, and gets to work and help people every day. It's just awesome. So you guys have all chosen well, and I hope as we go through the program, I can continue to build your love of nuclear medicine and help you love your job. So, and of course, pass your boards. That's the goal, right? So first off, just we'll get kind of a couple housekeeping things out of the way. First, can you guys hear me good? Okay, got a thumbs up. Thank you. All right. So for the next thing, I want to give you just kind of a quick introduction to myself. Like I said, my name is Michael Martin. I've been in nuclear medicine for about 16, 17 years. I went to the program that you guys are going through right now. I went to Weaver State, so I know exactly what you guys are dealing with and what you're going through. So I can have all kinds of empathy for you. When I first graduated, I was hired at Intermountain Medical Center here in Murray, Utah. It's a level one trauma center, and it's kind of the biggest facility in Utah. Um, right when I initially hired on, I worked in nuclear medicine and I worked in oncology pet and cardiac pet. And at that facility, they were all kind of combined together. And then what happened is over time, the departments kind of separated out. Cardiology and nuclear medicine kind of wanted to do their own things. And so they made us techs kind of choose. And so I went to the nuclear cardiology side of things. And that's where I've been ever since. So that's where my head is kind of now. I'm going to check my iPad really quick. I'm hearing like an echo. I have an iPad on because I use it for a whiteboard, but there we go. I think that's better. So anyway, yeah, so that's me. Right now, the cardiac center that I work in, we run two PET scanners. We do about 25 to 30 patients a day, so I think we're one of the busiest cardiac PET centers in the country. And then I'm serving right now as in a lead tech role, and so just have a lot of experience that I hope to be able to bring to you guys. Let me make sure everybody's muted here. Still getting a weird echo. Are you guys getting a weird echo? Yay, nay? Let me see if I can mess with this now. For some reason, I can see you, Joe. I see you, and you're like white on my screen. That's the only one I see. So welcome, Joe. How you doing? All right, but everybody can hear me. We're good. As long as you can hear me, I guess we're good. Joe, you're gonna have to give me the thumbs up because you're the only face I see right now. Oh, Tori gave me a thumb. I like it. Okay, excellent. Somebody's saying no, no. I'm guessing you guys don't hear the echo. Okay, I won't worry about it too much. Hopefully that doesn't drive me nuts. We're getting lots of them. Okay, awesome. So my first question is I've got a lot of intro stuff, but I sent you guys out a video. If you logged on to Canvas, I sent you an intro video. Can you guys give me a general idea, maybe with just some thumbs ups on the text? Who had a chance to watch that? I don't want to double cover, and we have a lot of stuff to cover. I don't want to waste too much time. Who watched the intro video? Getting lots, 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 lots. Okay. I'm thinking that's probably the majority of people who are on here. Okay, cool. All right. So what I'm going to do is I'm going to do like a very, very brief overview of Canvas, just really quickly to make sure that we've covered all that. And then we can also just kind of answer any questions that you come up with during that. And then we'll move on. They've slotted us with 2 hours and we have a lot to cover. So we'll try to get into the meat of what we're going to cover today right away. So let me go over to my Canvas and I will share my screen and we'll see what we got here. All right, can you guys see my Canvas page there, the home page? Okay, I got a thumbs up from Bethany. Thank you. All right. Okay, so like I said, most of you have been through this, so we'll go through fast. Really what I want you to know is kind of what's in the course and how to kind of do your homework and start to do everything. So, well, obviously over on the left-hand side, I've got everything listed. We got our syllabus, quizzes, assignments, Zoom, and grades. Pretty simple. I put the syllabus on here. If you've looked at the syllabus, the main thing you're going to see on the syllabus is dates, right? So that's when we're meeting for class. That's probably kind of the most important thing is to have your dates on there. So also there's textbooks on here. And so that's kind of what I have on here. And then just the general how I'm going to grade. Does anybody have any questions on the syllabus? Again, I'm not going to go through it because I did on the intro video, but do you have questions about the syllabus? Okay.
Which book do you choose, do you tend to pull your questions from? Like, which book do you heavily prefer?
So the book that I kind of try to follow, I'll put it this way: the book I follow in my lectures, I teach a couple of chapters out of the book, and it's the Waterstrom book. So that's kind of probably the main book, and then Medler and O'Malley are kind of your supplement books. Um, Really, the books they cover the same stuff, and they're very similar, but they're slightly different in some of how they explain it. Um, so it's going to be, it's just better for some of you will kind of how one book describes or teaches is better than another book. I will tell you that Waterstrom is the main text, but it's very, very detailed. And the other thing I try to do is in my lectures, I try to take that detail and distill it down to what I think you actually need to know. So when you go through the module for this course, it's going to point you to where to study. I want you to go and study those things. Um, and then I want you to use my slides and my lecture as well to grab for both of those. So I pull from them all, but I will say that your general main, your kind of Nuke Med Bible is the Waterstrom text. Did that answer your question?
Yes, thank you.
Okay. Let me hit the chat here. Someone in the chat, Kyler, he said, so exam one and math quizzes will be due before next class. Yes. Now, what you will notice, Kyler, is I don't have due dates on there. I have opening dates for the quizzes because I don't want you to take the quizzes before my lecture. But I don't have due dates on there. What I would like you guys to do is keep up with the schedule. So you're going to have your after the lecture, your exam for that section will become available. What I'd like you to do is study everything before you come to class. So you've got a bunch of study in your brain, and now I'm going to distill it down in my lecture and then allow you to ask questions during this time. And then you'll be ready to kind of go take the test. That's the hope. Okay. I understand. I remember I lived your life exactly. I know when I was doing this, I was newly married with a baby on the way. Um, I had to work. I had to, figure out how to pay for rent and everything else. Plus, you're doing your school, and you have many other classes besides mine. Plus, you all have clinicals. Like it's ridiculously busy. So the reason I don't put the due dates on is because I know that your life's crazy and you're going to do the best you can, and I'm just going to give you the grace for that. However, please try to keep up because you're going to make your stress worse if you put it off, put it off, put it off, and now at the very end we're trying to make up everything. Also, that's really not very helpful in the learning process. Nuclear medicine is kind of building block. You need to build upon itself. So you need to be able to, keep up on things. So do your best to keep up would be my request. No due dates, but that's kind of how things will go. Hopefully that answers your question, Kyler. Okay. So yeah, so that's the main thing I want you to know about syllabus. If there's no like general questions about that, I think you guys have a good grip on what's happening there. The other thing I will try to do is I'll put my slides on Canvas. Somebody texted me last night, and I'm grateful for that because I thought I had actually put the slides on already, but I hadn't made them active. There's on Canvas you have to publish it, so I had them on there, but I hadn't made it active, and I meant to do that. Usually I try to get it a couple of days beforehand so that you guys have the slides. If some of you like to go through the slides on your own device as I'm lecturing, and that's totally cool, or print them out and make notes on them, that's fine too. So I'll try to have those available. The reason I don't make them available way in advance is because I'm constantly like trying to figure out better ways to teach you. And I feel like every time I've been doing this for probably this, I think you guys are my sixth group of students, maybe my seventh. But I'm constantly like tweaking a slide a few days before I lecture just to try to get it right and teach you in a better way. So that's why I do it that way. So hopefully you guys can work with me. I'm trying to be a better teacher all the time for you. So, all right. So that's syllabus. I'm already getting too wordy. Quizzes. You're going to have the quiz section. That's where all of your math tests are, your math practice, and then also the exams for each section. With the math, the thing that I will say here is we're going to go over some of that today. Hopefully, you've also had a chance to watch my video about radioactive decay. And so this is where you'll access those. What I've done in the math quizzes themselves as you try to take them is I've allowed some space for answers. When you're doing the math, it depends on how many decimal places you use. What I'm going to say as a rule is try to use 3 decimal places, round to 3 decimal places. That's what I've tried to do when I did the math and had to put the answer in on Canvas. Canvas allows me to give you a little bit of a range. So again, if you're slightly one way or another, you should still get the answer right. Again, if you don't get the answer right and you've gone through it a few times, contact me. I'll look at it. I'll look at yours. We'll talk. I'll help you see where you're either making a mistake or where maybe I had something wrong in Canvas. That's happened before. So just let me know. Let me see. Could we get them maybe the Monday before class if you don't? Yeah. Ashley, I can try to do that. Get them to you the Monday before class. I'll try to get them to you as soon as possible. That's fine. Okay, let's see. What else did I want to show you in here? Let's go back to homepage really quick. You obviously know where the Zoom classes are because if you didn't know that, you wouldn't be here. So I won't go over that. And what else do I want to go over? Does anybody have any questions on how the module works? Hopefully that's pretty simple. Again, it's just designed to point you to, it gives you the section, it tells you where to look and where to study. If any of you ended up with the 8th edition of the Waterstrom, again, the chapters are slightly different, but if you look through there, you should be able to find it. It's not too hard. Okay, I'm guessing no questions on that. Other than that, I think that's all I wanted to cover. Oh, the other thing I wanted to make sure you guys understood correctly is when you take your test, and your test will be available today, I want you to do them closed book. You have to pass boards at the end of this. And so I want you to do them closed book so you start getting used to taking tests. I've provided so that when you miss a question, you get to do test corrections. So the way test corrections will work is everything that you got wrong on the test, what I want you to do is you're going to give me a document that lists what questions you got wrong, the correct answer to that question, and then just a quick reference of where what book you found it in or a page number or something like that. That's going to allow you to get a better grade. But as I said on my introductory video, I actually believe that it is a part of the learning process. And it's one of the most powerful processes to learn. Because when you have to go and specifically study what you missed and find it and research it, it puts it in your brain. So I would ask you, I can't make you do test corrections. And the reason I can't is because everybody's going to miss a different amount on the test. And so there would be no way for me to give a point value to that would be fair. So instead, I give a half a point extra credit for each one of those that you get, but everybody's different. So I can't make you do them. If I could make you do them, I would. So please do them. it's kind of like what I said with when your tests are due. I don't make due dates, but please try to keep up. Please do your test corrections because it's part of the learning process. I've designed it that way. That's part of the design of the course is to go back and look at what you missed. Okay. Any questions on that? Okay, and take that also as a no. All right. Okay, any other questions in general? If not, I want to get talking here. Okay, let me get my slides pulled up and we will get moving here. Sorry, let me try. My computer's having a little issue here. Let's try that one. Okay, can you guys see my slides? Let's see, I can see you and Sharon, I can see your face right now. Will you give me a thumbs up? Okay, perfect. Okay. All right, and then I'll try to pay attention. Oh, this is the other housekeeping thing, you guys. Once I start lecturing, I'm not really great at paying attention to the chat. So, what I would ask of you guys is just somebody bug me. If there's something in the chat that I need to answer, just somebody bug me. I'm totally cool with that. I want you guys to interrupt me. Like if you have a question or anything during this and I'm teaching, I tend to get talking and I'll ask a few questions along the way, but I just tend to go and get focused in on my slides. So if you have a question, literally just like mid-sentence, interrupt me. I don't care. I'm totally chill and easy. It's no big deal at all. You can just jump right in. Okay. All right. Okay, so this is we're going to cover physics and math today. This is your goes with your module in section 1. And honestly, like the physics of nuclear medicine is one of my favorite parts. I geek out about it. I don't know why you guys all chose nuclear medicine, but one of the reasons I chose it is because I'm just kind of a nerd. So hopefully you're my fellow nerds, and I just geek out on the physics part of this. It's just what we do in nuclear medicine is so cool. So I wanted to start out with this slide. This is kind of my first geek out slide that I just find a little bit mind blowing. So what you've got here is you've just got a scale of size. And so I want to open up your minds to what we're dealing with in nuclear medicine and the scope of it. So if you look on this chart, you've got this man here, right? So he's probably like 6 feet high. And this is measured in 10 to the 0 is kind of at 0, right? 10 to 0. So if you've got right in here, so they're saying he's probably around 6 feet high. And if you don't understand this scale, what it means is 10 to the 0 is just 1, and 10 to 2 is 20. It'd be 10 times 10 is 20, and we'll go over a little more of that. But that's where the scale is going, right? So you get to a football field, and you've got 10 to the 2. You're getting a little bigger, and so it'd be 10 times 10, actually 100, not 20. Sorry, I said that wrong. Anyways, so you've got something small, and you're working at big. You've got the size of the Earth, and what I want you to recognize is you go up to our solar system. You get clear up to our galaxy, right? So this is like our entire Milky Way. And you're somewhere up just above 10 to the 20th. You're probably somewhere between like 10 to the 21st. Okay. So that's huge. Now, I don't know about you guys, but I go out at night and I look at the stars and I'm just like, wow, this is insane. Like there's so much out there and it's such a vast distance. We can't even reach the stars. We can't even get there, right? They're so far away. So the galaxy is just mind-blowingly huge. I mean, I don't think we really can even comprehend it. Now, in nuclear medicine, that's going up in size, right? But in nuclear medicine, we deal with things that are really, really small. And so what I want you to notice here is if you go all the way down to the nucleon. So what's a nucleon? We're going to talk about this today. It's like protons, neutrons. electrons. The nucleons are as small as our galaxy is big. So that's the scope of what we're dealing with in nuclear medicine. That just blows my mind. Like the things we're dealing with are that small and that tiny. And I just think it's crazy, crazy cool. So the question is, how small is an atom? So these are a couple just gee whiz facts. These are not like testing things, but if you took all the people on Earth counting one atom each second, it would take an excess of 30,000 years to count the atoms in a drop of water. That's how much there is. Another one, there are more atoms in a glass of water than there are glasses of water in all the oceans on the Earth, right? So we're dealing with it's amazing the scale of things we're dealing with in nuclear medicine. I remember when I was in X-ray, one of my teachers told me, they were talking about, I always wondered, like, how can X-rays penetrate the body? Or we're going to talk about gamma rays today. How can gamma rays penetrate the body? Like, how does that even work? Someone told me that if you took a basketball and a basketball represented the nucleus of an atom, that the first electron would be 2 or 3 miles away, right? And when I learned that, it was like boom, like I understood like there's so much space in there. No wonder, gamma rays and photons and things can pass through you because there's actually tons of space. So it's just really cool. What we deal with is awesome, and the physics of it is really cool and kind of mind blowing, honestly. Okay, so what I want to talk about here is energy. So when we think about X-rays and gamma rays and the things that we look at in nuclear medicine, what I want you to understand is energy. They're just energy. Everything is just energy. Energy is a product of wavelength and frequency. So if you look at this wave down here, this is a sinusoidal wave, and this is the way that energy works. And if you think about it, energy is just light. The most common one we think about is light, because light is what we use to see. We've been around it forever. And so that's on the energy spectrum, right? Visible light is sitting right in here. You start down here with radio waves and work all the way up to gamma rays. What I want you to pay attention here is that the wavelength and the frequency, the greater wavelength and the greater frequency is the greater energy. So what frequency means is frequency is every time this sinusoidal pattern passes the midline, that's how frequent it's happening, okay? And then your wavelength is from one wave to the other. And so they kind of have an inverse relationship. But what you'll notice is that as the frequency gets greater and greater, you get tighter and tighter. And what ends up happening is you have a stronger and stronger form of energy. So radio waves really weak. We work up to microwaves, visible light not so strong. But as we get up to X-rays and gamma rays, what I want you to notice is that pattern of frequency. And again, this is just a picture to try to represent. It's not, to scale or anything. But that gamma ray, what I want you to know is it's so tight and so bound together that when we talk about it in nuclear medicine, we call it a photon. And we say that as though it has mass, like it's a thing, but it's not a thing. It doesn't have any physical form. It's just energy. But because of that tightly packed energy, we talk about it and we say photons or we say gamma rays. And we'll talk about it as though it's a thing, but it's not. But just understand that it's very, very, very high, almost like packets of energy that are coming through and doing some of the things that we talk about in nuclear medicine. Does anybody know the difference between an X-ray and a gamma ray? I know a lot, most of you are X-ray techs and you've been through some of this physics. What's the difference? Who wants to shoot at that one?
The origin of where it comes from.
Tell me what you mean by that. Thank you for jumping in too. Who was that?
Bree.
Bree, thank you. Tell me what do you mean?
X-rays come from the electron cloud and gamma rays come from the nucleus of an atom.
Yeah, exactly. You're exactly right. So those of you that have been in X-ray, you've talked about the cloud interactions and everything that happens. And we talk about some of that in nuclear medicine, but now we're going to get it down into the nucleus. Gamma rays come from within the nucleus. That's exactly right. All right, so what I want to talk about, we need to talk about there's 3 energies associated with the atom, and understanding these energies will help us as we begin to talk about radioactive decay and how it works. Before I go over these, I want you to pay attention to these 2 graphics over here. And we're going to talk in a minute specifically about protons and neutrons and electrons, but I just want you to generally have this in your mind that, so typically, and there's kind of a couple ways that to look at this. This graphic shows things. You've got the nucleus and you've got the electron shells. And depending on, science kind of updates from time to time and figures out things. Physics do that as things are learned. But you kind of have a couple of models that you look at. One of the models looks like this, where it's almost like the solar system, almost like the sun in the middle and the planets circulating around. That's one of them. Another model that's been proposed that could be more accurate, we're not really sure, is you've got the nucleus in the center, and then you've got clouds around, or kind of cloud shells, and that it's not necessarily circulating like a universe, but the electrons still have motion and energy. For our purposes, what we're going to do, it doesn't really matter which one of those you use, just as long as you understand that we've got protons and neutrons in the nucleus, and then we've got electrons within shells coming out from the nucleus, and that those things have energies, and we'll talk about them, okay? So the first general energy that I want to mention is what we call strong nuclear force. Some textbooks will define it as nuclear binding energy. And this is the energy that holds the nucleus together, okay? This energy is one of the strongest energies in the universe at short distances. So really, really hard to pull apart the nucleus of an atom to get protons and neutrons away from each other. But once they're away, it actually doesn't have that much strength. It's easy to happen, right? So there's this balance that has to be kept within the nucleus. And one of the things that does that is the nuclear binding energy. And we'll talk more about other things happening in that nucleus. The next one is electromagnetic, or sometimes it's called electron binding energy. You may be familiar with this a little bit from X-ray, but this is the positive and negative charges that attract. And this is electrons. Electrons have a negative charge. In the nucleus, protons have a positive charge. And so this is the attraction between that negative and positive charge. This is highly dependent upon the proton number and the distance separating them. So when you have a nucleus that has lots of protons, it's going to have a lot of positive charge in that nucleus. And so those electrons are attracted at different distances and different strengths, okay? This is what we call those distances and how much attraction, we call that characteristic. It's characteristic of a particular atom. So if you're looking at technetium, or you're looking at I-131, or you're looking at rubidium, whatever you're looking at, those, because of the different protons within the nucleus, the characteristic attraction of each one of those shells of electrons is different. And you've probably heard a little bit about that in X-ray, and we'll reference some of that. The last one is kinetic or centrifugal, and this is the energy or the motion or the orbit, whichever way you look at it, of the electrons, right? The electrons have motion and they have energy. The closer an electron is bound to the nucleus, the more of its own kinetic or centrifugal energy it had to give up to stay there, okay? So anything that's the K shell, those electrons are less energetic than the L shell or the M shell, or working out how many shells you have, right? So your most energetic electrons are out on that outside when you talk about their kinetic energy. Now the binding energy, though, what binds them to the nucleus is very strong the closer it is to the nucleus. But remember, the electron had to give up energy to be close, but now it's very, very tightly bound to that nucleus. Whereas something in the L shell, it didn't need to give up very much of its energy, so it has a lot of energy, and it has a weak binding to the nucleus because it's far away. Okay, so those are the three energies that we need to think about as we go forward. Okay, so I want to talk about some subatomic particles and get specific about these nucleons. So within the atom, we have a proton, neutron, and electron. That's what we're going to focus on today. And so what I wanted to put on here is, first of all, I really like this chart because it kind of breaks down characteristics, and that's what I want to look at right here, is what are the characteristics of these subatomic particles. In this first one, I just put particle or energy. And the reason I put that is because when we talk about gamma rays and X-rays, we're talking about energy. Everything here is an actual particle, right? So it has mass. So that's the first thing. The next thing is we're going to talk about charges. So a proton has a plus charge, an electron has a negative charge, which I mentioned a minute ago, and then a neutron has a net zero charge. Now, I'll explain this more, but a lot of times when you take physics and you hear about a neutron, they just say it doesn't have a charge. That's not exactly true. It has a net negative because there actually is a positive and a minus charge associated with a neutron. And we'll talk about understanding that, and that's very important when it comes to nuclear medicine and radioactivity. So we'll talk about that more. But just remember, it has a net neutral charge or a net zero charge. Okay. You'll notice the mass on here of protons and neutrons are very similar, right? There's a little bit of difference. So this is kind of the weight or how big it is. And then you'll notice that the electron is quite a bit smaller. Now, even though an electron is smaller, its negative charge is just as strong as a proton's positive charge. Okay, so those charges aren't different, but the size of these things that we're dealing with is a little different. Okay, and so then I just wrote the charge again down here. And then the function is important as well. So protons make up the physical characteristics, and we're going to talk more about this. But a proton defines what element you have. Okay, that's all based on the number of protons. Neutrons are what determine nuclear stability. So that's going to be important. We're going to learn what does it mean when something is radioactive? What is it trying to do? What is nuclear stability, and how does neutrons affect that? They're the main responsible party. And then electron covers chemical properties. Now in nuclear medicine, we're not going to look at chemical properties much. If you've ever had a chemistry class, you've gone over properties and bonds and covalent bonds and all those things of how elements chemically work together. But that's the main job of electrons, and really won't cover a lot of that in nuclear medicine. Now, when you see an atom, or in a minute here, we'll talk about nuclides. When you see these things, you're going to have this is the way that they're identified. Okay, so you'll usually have in the middle, you'll have a letter that's the atomic symbol. So if you've already started working with technetium in your clinicals, so your technetium is Tc, right? So that would be what's in the middle. Carbon is a C, things like that. So that's going to be your sign right in the middle. One of our most important numbers that we look at today that we'll talk about is going to be this atomic number. It's the Z number. This represents the number of protons, okay? So the Z number, atomic number of protons. You need to memorize that. The A number is the mass number, okay? This is the total number of protons and neutrons. Both of these are relatively important in nuclear medicine. The other one is the N number, and it's usually subscripted to the lower right. It's the number of neutrons. Now, a lot of charts and things that you look at do not include this N number. We don't see that very often. And the reason that it often isn't included is because if you know the proton number and you know the mass number, because the mass number is the total of the Z number and the N number, you can infer the N number by knowing these two. So often that's not there, okay? And you'll notice that that's the case. Now, also the other thing that you need to know is the mass number. Sometimes a mass number will be placed after the atomic symbol. A good example is often you will see technetium 99, right? You'll see Tc 99. That 99 is the mass number. So sometimes you'll see it to the upper left, sometimes you'll see it in front. Typically, if it's to the upper left, it'll be subscripted, so it'll be smaller text. And if they put it to the right, it will typically be the same size text as the atomic symbol, okay? So you just kind of have to pay attention to that. But as you go through nuclear medicine, you'll see so much of that you'll know that. Just remember that 99, that's the mass number, okay? And then again, atomic number is the Z number scripted to the lower left. Okay, any questions on that? Okay, I don't see anybody in chat, so we're good to go. All right, so now we need to talk about nuclides, okay? So you guys are used to talking about elements. You probably had other science classes where you talked about an element. So the question is, well, what is it? When I say nuclide, what is a nuclide? Because sometimes there can be confusion between, well, this is an element and this is a nuclide. For example, technetium is an element, right? You can see technetium on the periodic table. Nuclides, what they essentially are, and as we get through the next few slides, you'll get a better idea. But for a simple definition, nuclides are variations of different elements. I would look at it this way. If your periodic table of elements was a map of the United States, Nuclides would be the states inside that map. So in other words, if I look on the periodic table and I see just technetium, and it will be there, when I go to nuclides, you're going to see things like technetium 99, technetium 98, technetium 97. So nuclides are variations of an element, okay? And there can be types or different types of nuclides. So we're going to talk about isotopes, isotones, isobars, and isomers and what those are, okay? So isotope, the first thing I'm going to have you look at right here is that I highlighted this P. And the reason I highlighted the P in isotopes is this is just to help you memorize this, but isotopes have the same number of protons. Okay, that's why I highlighted the P. Good way to remember isotope. You'll notice none of the rest of these have the P. Isotope, same number of protons. So same number of protons, but varying numbers of neutrons. Now, in the previous slide, I had said that protons define the element, what the element is. So what that means is that when we have isotopes like technetium 99, 98, 97, it means they are the same element, but they're nuclides of one another because they differ in the number of neutrons, not the number of protons, okay? They have the same atomic number, which is the Z number, but they vary in their mass number, which is the A number, upper left. They can be stable or radioactive, and they're symbolized by the superscripting the mass number, again, to the upper left, or by hyphenation in front like this, TC99, okay? So all elements on the periodic table have one or more isotopes, one or more versions of them. That's why I said it's kind of like a map of the United States is one thing, but then you can drill down in and look at the states, right? And get the difference in each isotope. So that's what an isotope is. So let me ask you this then. When I go from technetium 99 to technetium 98, did I lose a proton or a neutron?
Neutron.
Neutron. That's right. Who was that?
It was me.
You didn't pop up. What's your name?
It's Medeja.
Medeja. Thank you. You're exactly right. You lost a neutron, right? Because if we would have lost a proton, we would not have the same element. And isotopes are the same element because, again, protons define the element. So great job. Thanks for going out on the ledge and answering there. Okay, so the next one is isotones, and you'll notice I highlighted the N. So this is an equal number of neutrons, but different number of protons. So when we have isotones, we actually have a different element, okay? And again, remember N, different number of neutrons. Isobars are a different number of protons and neutrons, but the total number of those two is the same. So they have the same mass number, the same A number, okay? So that would be like your 99. So you might have a technetium 99 and a rubidium 99. Those are isobars, so because they have the same mass, right? Different protons and neutrons, different element, but same mass number. Okay, so that's why I circled the A. And then the last one is isomer. These have the same number of protons and the same number of neutrons. The only difference they have is they differ in the amount of energy present in the nucleus. And I'm going to define these better later, so don't kind of put those on a shelf for a minute. But while we're here, I highlighted Me because these isomers are referred to as metastable. And I will go over what metastable means later. But oftentimes when you're in the course of your work and you talk about technetium, you're going to see technetium is often labeled with technetium 99M, and that M stands for metastable. I will define that better in a minute because we need to know a couple other principles before we get to what metastable means. But just know that that's what that means. That's technetium 99M. A lot of things that are metastable don't always put the M on there, but you often see tech that way in our field. Okay. So try to memorize those. Those will be on your test for sure. And hopefully I gave you some things to kind of help that memorization. All right. So the next thing I want you to look at here, that you're used to looking at the periodic table, right? I want you to first look at this lower left table. This is not the periodic table. What this is called a chart of nuclides. So they set up these nuclides that I just described, those isotones, isomers, isobars, in a chart, and the chart's arranged in a certain way. So I want you to notice here's your technetium-99, here's your tech 100, tech 101, tech 98, tech 97, right? So what that means is that the column's going this way, and this graphic over here defines this. But going from kind of this horizontal way, these are isotopes. So anything we see together is isotopes. So here's molybdenum, technetium, rubidium. Okay, these are isotopes. When we go the other way, we have the isotones. Okay, so this is same number of neutrons, but remember different protons. So what do we have? We have different elements, right? Not the same element, but the same number of neutrons. Okay, and then at an angle, we have the isobars. Okay, so you'll notice here, again, the mass number is the same. So molybdenum, technetium, rubidium, 100, 100, 100. Okay, we're going to come back to this chart when we start talking about radioactive decay and what's called a parent-daughter relationship. We'll do that in a minute. But this is what the chart is generally arranged this way. And then what happens is this chart is set along something we call the nuclear stability belt. Okay, so look up in the upper right-hand side. All these little boxes represent those nuclides along a belt. And I'm going to go to the next slide to explain this because it's a bigger picture, but we can kind of come back and forth. This is where we're going to start answering the question, you guys. What makes something radioactive? Why is it radioactive? What's happening? What is that element trying to do? And that's going to be answered here. Okay, so this chart right here, kind of the yellow, is the same here. This is just kind of more simplified out so we can talk about the parts. Okay, so we call this a chart of nuclides. Over here on your y-axis, this is the number of protons. Okay, so they arrange these, they place these nuclides on this chart that with lower number of protons all the way up to the higher number of protons. So if your element has lots of protons, it's going to be higher on the chart. And then on the x-axis, we have neutron number, same thing, low neutrons to high neutrons, okay? This center line right here, this is what we would call in a stability ratio, a perfect stability ratio. And here's what I mean. When you have within the nucleus, remember we have neutrons and we have protons. And remember, protons have a positive charge. Now, if any of you have ever taken two magnets and you put it on the positive side, and you can do this with the negative side too, but since we're talking about protons, you take those two magnets, both on the positive, try to put them together. What happens? They push apart, right? You've all done that as kids. We're like, oh, cool. I remember like Back to the Future, hoverboard. So anyway, you try to push those together. I'm just showing how old I am now. That was one of my favorite shows when I was a kid. So you're pushing those together and they repel, right? So the protons within a nucleus are going to want to do the same thing. One of the things the neutrons do is they provide enough space so that the protons aren't pushing each other apart. Remember, I said that there's the nuclear binding energy that it holds it all together, but those protons are trying to also push apart from one another. So this is why the neutron is literally responsible for nuclear stability. It keeps those protons a safe distance apart. If you didn't have the neutrons in there, then your protons would want to come apart. And now, in my mind, I imagine we'd all explode, but that's probably not what would happen. But you get the idea, right? They go away. So what your nucleus wants to have happen is it wants to have an equal ratio to that positive charge. So that's what you see here is that at the very bottom or the start of this, you have a 1-to-1 ratio. So for every one proton, there's one neutron, right? To keep that balance. And if we were to go perfectly up at this 45-degree angle, that would represent 1-for-1 all the way up, okay? Now that's not exactly what happens because as you get more protons, as you get bigger and bigger elements, and those protons are getting so strong with their positive charge, it actually takes more neutrons to keep that proton charge from pushing apart, okay? So as you get higher and higher, it's probably somewhere in the neighborhood of around like, I think the textbook says around 38, it's a 1-to-1 ratio. And then anything above 38, it starts to get heavy towards the neutron side. And the reason it does that again is because it takes more neutrons to keep those protons a stable distance apart, okay? what is happening is right along the perfect axis of this, that ratio is in a good place. We call that nuclear stability, right? The nucleus is happy with its ratio. Anything below the nuclear line of stability means we are getting too many neutrons. We're too rich in neutrons. Anything above nuclear stability means we're too rich in protons. There's too many protons. So what the nucleus has to do is it has to say, I've got to do something to get to a stable place so that I can survive, right? I got to do something. And that's what radioactive decay is. We're going to talk about different versions of radioactive decay, but all radioactive decay is it's the nucleus trying to get to a stable place of numbers between those protons and neutrons to where all the electric charge there and the binding energy is happy and in a good spot, okay? Any questions on that? Did that make sense? I'm going to assume silence means it makes sense, or you guys can't hear me, or I can't hear you. I don't know. All right. Okay. So what I want to do next is I want to go in and start talking about the types of radioactive decay. So we've kind of set up, this is how a nucleus wants to, what it wants, and this is why we're having radioactive decay. Now, how does it do it? What does it do to get back to that stable portion? How does it work, okay? We're going to talk about alpha decay, beta minus decay, beta plus decay, electron capture, and then gamma ray. And we'll go through all those things. We'll mention internal conversion. Don't worry about that till we get there. But we're going to talk about all these different types of decay, right? So now we're trying to get into how it works. How does the nucleus get stable? So the first one we'll talk about is alpha decay. Okay, alpha decay is really, really big particles. These are very, very large in size. They're up towards the top of that nuclear stability belt. And usually these are like greater atomic numbers greater than 150. Okay, so lots of protons and neutrons. Sometimes alpha decay is called fission, nuclear fission, and you might hear that, you might see that in a textbook. You could say that. I don't think I put fission. Did I put fission on my test? I might have put fission on my test. I don't think I did. But I could see that being in your on your board. So no alpha decay also by nuclear fission. But basically what's happening here is to get to a nuclear stable place, because it just in this case needs to get smaller, it actually emits 2 neutrons and 2 protons. Okay. Radium-226 is an alpha emitter. I put that there. But you're getting rid of 2 neutrons and 2 protons. Now I want you to think, we need to start thinking about when we get rid of things out of the nucleus, what does that do to the nucleus and what does it do to our element? In this case, because we get rid of 2 protons, the atomic number, our Z number, which is the proton number, goes down by 2. Okay. Our mass number, which is the combo of protons and neutrons, right? The 99 number or the whatever, that goes down by 4, right? So both of those go down. So what I want you to think about right here, if my atomic number, again, this is the proton number, goes down by 2, do I have the same element still? No, Bree, thank you. You're right. Bree texted it or put it on the chat. Thank you. Yeah, you don't, right? And the reason is that, again, remember, protons define the element. So you've created a new element, right? So when this happens, new element occurs. Now, to understand in terms of what alpha decay does, alpha decay is a very large particle, okay? Usually you don't get 2 protons, 2 neutrons, 2 whole protons and neutrons coming out. That's large. Okay, so this has a very high amount of ionization in tissue. It's very damaging in tissue. However, it's really, because it's so large, it doesn't travel very far, right? It doesn't have a lot of push power, okay? So it can't even penetrate a thin piece of paper. It can't penetrate your epidermis, okay? So it's very, very damaging right where it's located. I would say it's, you think of a frozen lake, right? If I had a huge rock, I probably can't move that rock very far, wouldn't be strong enough. But if I got that out on the lake, it's probably going to break through the lake because it's so huge, right? So highly damaging, not very movable, doesn't have a lot of travel, okay? This is not useful for imaging. We don't image this in nuclear medicine. However, there are some applications. One of those is what we call a Xofigo. It's useful. Xofigo treats metastatic bone pain. So these are patients that we're not trying to cure their bone cancer, but they're probably more towards end of life. They have massive bone cancer and they're in a lot of pain. Xofigo treatments can go in and it can target the bone cancers, connect there, and then kill things off. And what that does is it reduces the pain down, brings the pain and the intensity of that down. And there's some other treatments. Xofigo is a little bit on the older side, but anyway, though there are some things we do with it in nuclear medicine, but there's not a lot that you do for it, and we don't image alpha particles. Okay. Okay, so the next one, so that's alpha. Beta has two types. We're going to do beta minus first. I'm going to try to give you another hook to memorize this one. This one's called beta minus, and you'll often see it written with a B and then a minus sign. This one is when you have an excess of neutrons. So we have too many neutrons. Nucleus has got to do something to fix that ratio and bring the neutron number down. Now, the reason I would highlight minus. A minus, when we think of minus, like in math, like 5 minus 4, whatever, it's that negative sign, right? So if you think of the minus sign, let that think of beta negative, and then neutron and negative start with an N. Okay, so this is how you can try to remember it. Beta negative, you're going to think of negative and neutron. We have too many neutrons, okay? So what happens here is a neutron is transformed into a proton and an electron. So it's going to pop out. It's going to take a neutron. It's going to go into a proton and electron. Now, this is why I mentioned to you earlier, when we talk about neutrons, we usually think of them as no charge. Again, remember that they're just net zero charge. They're neutral charge. And the reason is they have some positive and some negative in them. So what happens here is the neutron will break apart. It will kick out its negative charge in the form of an electron. That electron goes out of the nucleus, and that neutron now becomes a proton. So we've changed a neutron into a proton, got rid of an electron, okay? Now you'll notice here, again, what happened? We went up in our proton ratio. We went up in protons. So I'll ask the same question I did before. Do we have the same element? See if anyone texts. You can put it in me. No, yes, Olivia, right on. Thank you. No, we don't, right? Because our proton number changed. So this is what we call a parent-daughter relationship. So in beta minus, you have an element, we have beta decay, and that's the parent, and then whatever the element is left over afterwards is what we call the daughter, okay? So an example of this, and you'll learn this in your pharmacology class, but technetium is the daughter product of molybdenum. Molybdenum 99. You'll have at your radio pharmacy, they have a molybdenum generator, is what they call it, and you'll learn more about that in your other class. But that generator, as it decays, is what they pull the technetium off to send to you for you to use for your test. But it came from molybdenum because molybdenum decays with beta minus, and it turns into technetium. Okay, and that we call that transmutation. So that's another kind of term that you need to know, right? When you talk about transmutation, we're talking about going from a parent to a daughter. Parent to a daughter, transmutation. It changes, right? These travel about 1 centimeter in soft tissue, and they're not as damaging in tissue as alpha particles, but they're still damaging because they are a particle. This is useful in some nuclear medicine applications. One of those is I-131. So when you do I-131 treatments, so this is where people have a hyperthyroid, and the goal here is we need to calm that thyroid down so it's not so hyperactive and causing all kinds of problems with hormones. So you'll take I-131, and they usually will swallow a little pill. Iodine is attracted to the thyroid because thyroid uses iodine for part of its energy substrate. And so it'll be attracted to the thyroid, and that will, little bit of damage will kind of kill the tissue off and bring it down a little bit in its hyperactivity and relax it and bring it down to a normal activity level. Okay, so that's what we're doing when we do an I-131 treatment, a therapy treatment. We do not image beta particles, okay? So the beta particle that comes out, the only thing that comes out of that is this electron. We don't image that electron. So I-131 is not useful for imaging. Now, there might be some of you that are already in clinicals. I've seen someone put someone with I-131 underneath the camera and get a picture. That's because I-131 actually has a beta that pops off, and then there's some gamma that happens along with that, okay? Right now, I'm not focusing on that. In a couple slides, we'll define what that means and how you have gamma ray, what gamma rays are, okay? But for now, just know that I-131, speaking specifically of beta minus decay, the electron coming out, we can't image that, but it's useful in treatments. Oh, and one other thing I should mention here, and I have this written, I meant to mention this, I meant to mention this one. So you'll notice on the little chart over here where I have my graphic, and the book will talk about this too, but it talks about from the neutron, there comes the proton and the electron. And then it talks about this thing that they call an antineutrino. You don't need to memorize this for purposes of your boards and purposes of nuclear medicine. This is just the book being very thorough. What a neutrino is, just for purposes of explaining, when they would take and they would measure a neutron, and they would take kind of its mass, and then they would measure the proton afterwards and the electron separately. And when they put the proton and the electron together, it didn't quite equal the mass of the neutron. So kind of I would call it the latest scientific explanation or theory about that is what we call a neutrino. And they say the neutrino is a tiny particle that comes out. They say it really doesn't have a lot of mass. It doesn't really do anything. There's not really interaction, but they call that a neutrino. So it's kind of their latest explanation. That could change in the future. I don't know, but the book talks about it. I wish the book didn't talk about it. I don't think it's necessary, and I just guarantee you're not going to be asked about neutrinos on your board. But just understand when you're studying the book and when you're looking at the slide here, that's what this other particle is. And I mention it right here. The proton stays, electron and antineutrino are emitted. For you guys and for your memorizing purposes, beta minus is that neutron becomes a proton and an electron. Just end it right there, okay? And you'll notice the same thing in beta plus, which is what we're going to do next. All right, so beta plus, you could kind of think of it as almost the exact opposite of beta minus, and I'll give you the same idea in memorizing it. Is that beta plus comes from a proton excess. A proton excess. It comes from proton excess. Okay, so remember plus, beta plus. The word plus has a P at the front of it. Proton has a P at the front of it. Okay, so that's a nice little convenient thing. Neutron negative, proton positive. So this is beta plus. Beta plus is a proton excess. So again, if we have too many protons, we got to do something to equal that ratio out again. Okay, so in this case, instead of the neutron doing some transformation, we have protons that do some transformation. So the proton transforms into a neutron by giving off what we call a positron. Okay, now a positron is basically a positive electron, and some of you may have heard of that term before, and some of you may not have. Before nuclear medicine, I didn't know about that. I just had only heard of electrons. The reason we don't hear about positrons in a lot of other scenarios and cases, or even just in a general physics class that you may have had, is because the positron only exists for a tiny fraction of a second. They don't exist very long in our universe, right? They go away. And what happens is that when that positron comes off, it gets kicked out of the nucleus, it travels a short distance, and then it finds a free electron. And that electron and that positron, their plus and minus charges, are attracted so hard and so fast, they come towards each other and collide in such great force that they have what's called an annihilation reaction, okay? And what happens is that they hit so hard that their mass actually turns into energy, and it turns into two gamma rays going exactly 180 degrees apart, okay? They're always, this chart says 511 MeV because it's mega electron volts. If we move the decimals over, you'll mostly hear it say 511 keV, right? So the 511 keV photons traveling in opposite directions. This is actually what we image in PET. We image these two gamma rays traveling in opposite directions, but that's what happens in beta plus. So again, you're going to get an atomic number that decreases by 1 because again, we're proton excess and we change the proton into a neutron and a positron. So we came down in our proton number. So again, there's a parent-daughter relationship that happens, which is the transmutation. This requires really high energy, but that's those two electrons coming together have enough energy. And then this is useful in PET. It's what we do in PET. Okay, so that's beta plus. So you need to know that one as well. And again, guys, remember, if anything's not making sense, just interrupt me. Interrupt me, because I guarantee you, if you're thinking, oh, I didn't get that, there's probably several other people in the class that are doing it. So interrupt me and we'll explain again. Okay.
You
All
said
right.
it has to interact with a free electron, so it won't interact with one in another atom's electron cloud.
Yes, so it can go find one in an electron cloud, or just free electron, just anywhere that it can find an electron, it will find one.
Thank you.
Mm-hmm. All right, any other questions? Cool. Thank you for interrupting me. Really, guys, like I'm all about the interruptions. Okay. Okay, let's talk about electron capture. So electron capture, I don't have a fun little thing to memorize it, but hopefully as we talk about what's happening in electron capture, it'll make sense to you. So this is going to be a proton excess. Okay, we have proton excess. What happens in electron capture, instead of like a beta plus decay to get rid of proton, what happens in this case is the nucleus will reach up and it will grab one of the K-shell electrons and it will bring it in to the proton to now form a net neutral charge and become a neutron. Okay, so it reaches up and grabs one of the K-shell electrons and pulls it down in, okay, and stabilizes that way. So with that, we have our proton number going down by 1. So again, we have the same thing. We have a different element. We have the parent-daughter relationship, but that is captured. Now, a couple other things that happen in this that we need to kind of define is that, and you guys will kind of be used to this in some respect from X-ray, but we have what's called a characteristic reaction, or a characteristic X-ray given off. And what that means is that this K-shell has to have, and each element is different, but it has to have a certain number of electrons in that K-shell. So if an electron gets grabbed out of that K-shell, what will happen is the shells above it are going to now, one of their electrons will drop into place in that K-shell, and that reaction will will have that same process from each shell coming up. Now, you guys learn that in X-ray because you're used to what's called characteristic X-rays, right? You've used those in X-ray. And so what you do is you get a little bit of characteristic X-rays given off. So you end up giving off some gamma, you end up giving off some characteristic X-rays. This is somewhat useful in imaging in I-123. I-123 is an electron capture. And the reason we can use that for imaging is it gives off a little bit of a gamma, but you can also actually, depending on, specifically for I-123 because of its K-shell energy, you can actually image that. You can tell your camera to look for that energy level, and you can do some imaging with that. Most of the time, though, this just gives off characteristic X-rays, and it's more exposure to the patient. So we don't use a lot of things with electron capture in nuclear medicine, but I-123 is one of those that gives off by electron capture. Okay.
How does it give off gamma rays?
Good question. I'm going to actually explain that in the next slide. I'm going to hold that off, but we're going to talk about how gamma ray happens, and then this will make sense a little bit more. Is that okay?
Yes.
Okay, but it's a good question. It's a good question, and I debated earlier, like years ago, I debated not putting this in right there, but I wanted to understand that I-123 is a good example, and you can image both of those. But let me get to that, and it'll also help answer the reason why you can also take I-131, even though it's a beta minus, you can put it under a camera and get image. It's because of the gamma rays. But let's go there next. So I'm going to move on from this one unless anybody has answers, but we'll answer that next question with the next slide. Okay. All right. So we're going to talk about, you'll notice up here, I call this isomeric transition. The book calls it isomeric transition. It is gamma emission. Gamma emission and isomeric transition are the same thing. The book says isomeric transition, and then it will call it gamma. On your boards, it could be both. Understand that 99.99% of the time when you talk about things in nuclear medicine, you're going to say gamma rays or gamma emission, but isomeric transition is technically what that's called. And then we're also going to talk about something called that happens within gamma, which is called internal conversion. Okay, so let's identify gamma first, and hopefully this will answer the question on the previous slide. So in gamma emission simply comes from a nucleus that is in an excited state with excess energy. Oftentimes, so there's no change in protons or neutrons in gamma emission. And oftentimes this comes as a secondary reaction to something else that occurred, like a beta minus reaction. So the reaction occurs in beta minus, and that nucleus can simply just become into an excited state, okay? And to get rid of that excited state, it will simply just let that energy go after that reaction occurred. And that is actually what is gamma rays. So 99% of the times when you're imaging in nuclear medicine, you're just dealing with a nucleus that's excited, again, often because of a secondary reaction to another type of radioactive decay that just occurred, okay? Now, one of the things to understand is, remember, different nucleuses are different sizes. Like, what I mean by that is more protons and neutrons. Remember, we talked about the belt. When you're way up high on the belt, you've got a lot more protons and electrons. And so you've got more energy existing in that. And so the same thing happens with gamma. When it's excited in general, it has more energy. So different isotopes, or excuse me, I shouldn't say it that way, different nuclides that give off a gamma are going to have different energies based on that. And what that means is that particular isotopes emit different energies and therefore can be identified on the basis of that energy coming out. That is why, and maybe you've heard some of your texts talk about so far, but technetium-99 gives off 140 keV gamma ray, okay? That's because of the size of that nucleus and the energy that it can exhibit. It's going to give off 140 K. Whereas, you know, in I-131 has a different energy. All of them have different energies that they give off, right? So you're going to have different energies based on the isotope. So that's one thing to keep in mind in gamma emission. And when you put a radioactive source under what's called a spectroscope, your camera, and we'll talk about this in our next lecture, but your camera has what's called a spectroscope, and you can put, ask one of your techs to show you next time you've got a patient. You should have somewhere on your screen for your camera where you make your adjustments and start and everything. You should have somewhere that you can click and look at the energy that's coming off of the patient, right? And so most of the time, if you have them and they have technecium and you put them under the camera, you're going to see this spike. It's going to be right at 140 keV. And it's going to see that energy. So you could, if you found a radioactive source, like you've got your survey meter and you find a radioactive source, if you can get that radioactive source and you could put it under a camera or a spectroscope, you could measure its energy and identify what it comes from. Is this technetium? Is this I-131? What do I have under here by those energies that are based on, again, the size of that nucleus, okay? So with gamma emission, just remember, excited nucleus, and it just gives off that energy, again, in the form of energy. That's why we have no mass involved here. Remember I talked about earlier, gamma rays, we call them photons, which sounds like it's a thing. It sounds like a little circle coming out, right? But it's not. Like everything else, electrons that come out, all the other decays have something happening with a particle. Here we don't. We just have energy being given off. Okay, so again, that's why over here, to answer that question on an electron capture, that's what's happening. When this electron capture occurs and that electron gets pulled down in, it creates that neutron, but then there's excitation that's happening, and that excitation, when it settles down right after that reaction, it gives that gamma ray off, and that's what we can image in I-123. Okay. So within that gamma emission, we need to talk about what internal conversion is, okay? Internal conversion can happen in anything that gives off gamma. And essentially what's happening here is that remember I said the nucleus is giving off that energy, and that energy comes out, and we want to see all that energy because we use that to make our image, right? But as you can imagine, it being in the nucleus, it's got to travel a distance, and all that's around it is all those electron clouds. All of those electrons are there. So what can happen in internal conversion is that as that energy is transferring out, it can hit one of the shell electrons. Often they define it by the K shell electron, but let's say it hits that K shell electron, and it can knock that electron out. Okay, it can knock that electron out, and when that happens, we get more characteristic X-rays. Now that electron that gets knocked out, and this could be on a test, is called an Auger electron. Okay, so this happens in internal conversion when a gamma ray hits and that electron is knocked out of the shell. We call that an Auger. Okay, and again, with that electron being knocked out, we're going to get the characteristic reaction again, right? What happens is the kinetic energy of the electron will be equal to the gamma minus the binding energy of the electron shell. Now, I know that sounded really weird, so look back on this to get what I mean. But what I'm going to show you is this competes with gamma ray. It's something we don't want. Here's an example down here. This will help you understand what this sentence said, because I understand that's really jumbled. So if we take Tech 99 and we know it has 140 keV, so the energy is coming off the nucleus at 140 keV, okay? That 140 keV photon, 88% of the time, it gets out. 12% of the time, it's going to come in contact with that K shell electron, okay? What happens is the K shell electron binding energy, so remember I mentioned that there's a binding energy between the nucleus and the K shell. In technetium, that's a 21 keV. So it's being held there by 21 keV of energy, okay? So what happens is when that 140 keV hits that electron and hits it out, it took 21 keV of its energy to kick that out, which means that now your gamma ray that used to be 140 that now goes out, you're trying to image with, is now knocked down to 119 because it left 21 keV there to kick that electron out, okay? So that's why internal conversion is a problem. It's something we don't want, right? Because now this 100, when you have your camera, and we'll talk about this in our next lecture, you're going to tell your camera, I want you to look for 140 keV. I'm imaging a tech patient. That's all I want to see. I want to see 140 keV. I want you to look for that. But now you've got 119 coming out. Your camera's not going to see it. So all this is going to do is give exposure to patient. It's not great for our imaging, right? And so internal conversion is something we don't want. It contributes to patient dose, and it doesn't help our image, so it's not desired. However, having said that, all gamma emission is going to have some internal conversion. You can't get away from that, because if you have energy coming off the nucleus, it's bound to like interact with those shells at least a little bit. Again, remember we talked about the basketball and the electron? There's a huge amount of space there, which is why on tech, 88% of it gets out just fine, right? Because there's space, but some of it is going to hit those K-shell electrons and cause this problem, and that's what you're seeing here. We want something with high percentage, right? We want our internal conversion percentage to be low. In the case of tech, 88% of the time to 12, that's pretty good. Now, don't worry about, you don't need to memorize like internal conversion numbers for each isotope or anything like that, okay? This is to help you understand it. What I want you to know is what internal conversion is. For your boards, just know what it is. Like what it is, what's happening, what causes it. Again, it happens during that gamma emission, okay? Any questions about that? Okay. Why don't we take just a quick, I've got 10:14. Let's come back around let's just give it like 5 minutes. We'll take a quick break, just give everybody like a quick potty break, stretch break, and then we'll be back, okay? And we'll finish the rest. I'm just gonna keep the recording going and I'll be back. All right, guys, I'm back. We'll go ahead and get started again. Hopefully everyone's back and I'm not ditching out on anybody. I think it gave us about 5 minutes. So, okay. So before we kind of finish, I'm almost done with the physics portion, and then we're going to talk a little bit about math. We'll try to like hurry that a little bit because I gave you guys a video about the math already. However, my typical way that I do things is I will I will teach you all the stuff I need to. Actually, let me ask you it this way first. Do you guys have a class after this?
I don't.
Okay. Are there some? Is it pretty much? I don't think you
I
guys
think some of us do, but not until like 5:30.
Okay, got you. Okay, so what I typically do is we're slated for 2 hours, and so I only expect you to stay for the 2 hours. If we're getting close and I'm not done with my lecture, what I'll do is I will just acknowledge that it's time, and then I'll continue on with the lecture, and you're welcome to stay. But I understand you guys schedule your time, right? Like I had to do that at one point too. Some of you are like, okay, I got this from here to here, and then I got to go work and blah, blah, blah. So if you need to leave at the time, you just take off. I'm not going to, dock you or anything, and I'm not going to look down on you. You got to go, you got to go. I'm going to keep going until I'm done, and then this will be recorded and posted on Canvas. So that's kind of how I'll run it, okay? So all right, let's get going again since we don't have a lot of time left, and we'll just kind of get as far as we can here. All right. So that takes care of kind of the types of radioactive decay. Now, the other thing I want to look at, something that you'll see in textbooks, is what we call decay schemes. It's important to understand how decay schemes work and what they're representing. So decay schemes are just a way of visually representing what is happening in each of the different types of decays. And so you'll usually kind of have two planes. You'll have the X and the Y axis. The x-axis represents what's happening to the atomic number. So in other words, my protons. Are my protons going up or down? So if to the right, we're getting greater number of protons when we have decay, and to the left, we're getting rid of protons in our decay, okay? And then the energy is represented on the y-axis, and pretty much because we're decaying, we're always decaying or giving off some kind of energy, your scheme is always going to go down. So it's either going to go down and to the left, down and to the right, is kind of what happens with the protons. So for example, what you're seeing here, and also this is a good chart to recognize the representation for each alpha, beta, beta plus, beta minus electron capture. Sometimes you'll see a little a like this, and that represents alpha decay. And each of those are the same. The little b with the minus, b with the plus. EC will usually be electron capture. Gamma emission is usually represented with a little y. So when you see charts like this, sometimes they'll have those representations on there. But alpha decay, remember when alpha decay, we get rid of 2 protons and 2 neutrons. So when those protons come out, again, because atomic number is protons, we're going to go to the left because we're losing protons, going to the left and down in our energy. So when you see a decay scheme and you've got alpha decay, you're going to go down and to the left, again, by 2, and that's alpha. In beta minus, we're creating an electron, so we're going to go to the right? Or I just said electron. So you got to watch me. Sometimes I screw up. In beta minus, again, we're neutron rich, so we're creating a proton, right? Creating a proton, so we're going to go down to the right. And then beta plus is opposite. Remember, plus positive proton. We have too many protons, so in this case, in beta minus, we're kicking out a positron, and so we're losing a proton, so we're going to go down and to the left. Electron capture, we're grabbing an electron, which is negative, and pulling it in. We're pulling it in, again, to get rid of some protons and make that proton into a neutron. So we're coming down and to the left. And then a gamma emission, because we're not doing anything with atomic number or particles, that's just energy. It's going to be represented as straight down in an energy pattern, okay? So straight down energy. So that's what you're going to see on decay schemes. Here's another representation of that and what it might look like. In this case, it also shows like when we have our transmutation or our parent-daughter relationships, this one has, it's X representing whatever nuclide down to Y, which is a new element, right? When we lose it by that beta emission. So again, just another type of representation, but it's very similar to what is over here. Just a little bit different. And oftentimes you'll see it represented like this on a decay scheme. I want to look at some, and then also I mentioned earlier I would define what I meant by metastable, and so this is where we're going to do that. Okay, so we're kind of looking at tech and what its decay scheme looks like. I mentioned that you're probably learning this from Shauna, but it was made in a molybdenum generator, and so we're going to look from molybdenum what happens with our decay here. So first I want to define. Well, let's look at molybdenum, and then we'll define what metastable is. But we have molybdenum 99. We're going to have a decay, and what we have is 88% of the time we get this beta, right? Get the beta minus reaction, and that decays down to technetium 99, which is what you guys use most of the time. You'll notice that's an 88%. You notice the straight down line, that means molybdenum has a little bit of gamma that it gives off too, right? So beta decay, and it has a gamma that it gives off 12% of the time, eventually decaying in what's called Tech 99G. Don't even worry about this. I hesitated to even put the slide on because you'll never talk about this or need to know it. But just know that molybdenum is going to have that beta and some gamma it gives off. That beta is what decays down to Tech 99. And then to Tech 99, when it gets there, it now has the nucleus is super excited from all of that reaction, from the becoming a daughter, and it gives off a gamma ray. That gamma ray is the 140 keV ray that you measure all the time. That's what you use to make your images, and we'll talk more about making images next time. But you've heard techs probably say that gamma decay has a 6-hour half-life, okay? This is kind of what defines metastable. Now over here, this molybdenum, when it gives off the beta and gives off its gamma, this gamma doesn't have a half-life. It just happens. The energy just goes away. It gives off the beta, energy goes away, right? Anytime you have an extended period of giving off a gamma ray at a certain rate, that's what we call metastable. That's the reason technetium 99 is metastable, because it has this long half-life that we can actually measure and do something, okay? It's an intermediate state. Eventually that all decays and goes away, but in that intermediate state, we call that metastable because it's not stable, it's radioactive, but it locks into this time period where it's giving off a certain energy and we can use it, okay? So I kind of wrote that here. Gamma photons are emitted almost instantaneously after particle decay, but a measurable delay in the emission of the gamma ray photons is what occurs when we have something metastable. The intermediate state is called metastable, okay? So that's why you might see technetium 99M, but it just means that you have that half-life period that you can measure, okay? Metastable. And then don't worry about this. It eventually decays further into rubidium. But that's kind of what I wanted to show you is, again, you can have two things happening. Another example here is I-131. And this is what I mentioned with how we can image I-131, right? So 93% of the time, we get that beta minus. That's what we used to do a treatment with, okay? So we get that beta minus coming down. We do a treatment with that beta particle that comes off. But then we have this 364 keV. Again, this chart says 364 MeV, but move the decimals, make it keV, which is what we normally talk about. 364 keV. So technetium is 140, I-131 is 364, and you give that off in the gamma, and you can see that happening here. So again, two things happening. Beta comes off, then we're excited, and we give off our gamma. Okay, so that's I-131. So any nuclide that you look at and you pull up in a text, or you can find a chart like this, and you can see what's happening to it. It will define what kind of decay. Notice that it even has the beta minus sign right here. So it's saying it's decaying by beta, and then you know straight down is gamma. You could even know this by the arrow. You don't even need to have the sign there, because if you know it's going to go to the right, that means I'm creating protons. That's got to be a beta minus decay, at least with I-131. So anyway, but this is what you should look at when you're looking at charts. This is how to read them, how to look at them, okay? Any questions on that? Okay. The other thing I wanted to show you here, now that we've kind of gone through, is I want to go back to this chart. And you remember how I talked about how it's situated with the isotopes and different things. And we talked about this chart is also where you can see the parent-daughter relationship. Now that we've defined what transmutation is, and we go from a parent to a daughter, that you can see that on this chart. For example, and I'll use molybdenum again, because that's what our molybdenum generator right here is the parent of tech. Now, when we go for a parent relationship, remember that 99 is not going to change. And so we're going to shift up this way, and you'll look and you'll see that at the angle, it's an isomer, you've got Tec99. So these show parent-daughter relationships. So the parent is where it starts, and then the daughter goes out. Now this also will show you here in this chart, this is how it decays. So when you have alpha decay, you're always going to see it down and to the left from the parent. When you have a beta positive, you're going to see down to the right. When you have beta minus, you're going to see up and to the left, right? And we certainly see that relationship here with molybdenum generator producing Tec by beta minus up and to the left. So if you look at these charts, that's another way to view that. And you also can see here that this defines your beta and your gamma that's giving off and things like that. So that's what all of these little things are. You'll notice this one has IT, that means internal conversion. So it's talking about some internal conversion happens. It's a 6-hour half-life, 140 keV, and then it also identifies the beta. Don't worry about the hyper details here, but that's kind of what you're looking at on the chart. I want you to understand what it means to go from parent to daughter, what kind of decay is taking place, and you need to understand how those decays work, what is happening in those decays. Okay? Any questions on that? So that covers the radioactivity that you need to know. Radioactive decay, there's your physics. There it is. Any questions on any of that?
Sorry, which direction is gamma decay going?
So gamma on here, gamma is not represented on here because gamma is just the energy, and you don't create a parent-daughter relationship with gamma, right? You don't change elements. So gamma on a chart like this is going straight down. Okay, so this is just a decay scheme. It's telling you how things are decaying, like what the energy is. Remember, you have anything happen to the atomic number and the energy. So for gamma, it shows you the energy's going down in decay, but nothing happened with the gamma, or nothing happened with the protons. So if nothing happens with the protons, then we don't have a parent-daughter relationship, because parent-daughter relationships are only based on the element changing. And the only way it's going to change is if we've lost or gained protons. Does that make sense? So you don't see a gamma relationship on here. Does that answer your question?
Yes, thank you.
Perfect. You got it. Thank you for interrupting. Appreciate it. Okay, and I guarantee you there's other people out there like, oh, I'm glad she asked that. So, all right. So the last thing we're going to talk about with the physics side is just some interactions with matter. For the most part, in terms of creating our images, we don't get a lot of problems from extra interactions, scatter, those kinds of things that you're used to hearing about in X-ray. We have a pretty good way of keeping all of that out of our image. But we do need to just mention it because it's relevant in dose to our patients and things like that, okay? And all three of these, you've learned in X-ray, the majority of your X-ray, you've learned this before, so this is going to be fairly brief and they're not too hard to understand. But one of them is called the photoelectric effect, and you're used to thinking of X-rays doing this. Just know that now the gamma ray is the thing doing this, right? So when we talk about this incoming photon, it's going to be probably an incoming gamma, right? So and this is in tissue. So incoming gamma comes in, and typically what you have happen here is you've got a K-shell electron that gets kicked out. When that electron gets kicked out, we have a characteristic reaction where the electron above will come down and fill the shell, right? And that's going to give exposure to the patient. That doesn't help our imaging. And so that's an effect that can happen with some of our stuff in nuclear medicine with those gamma rays, especially with gamma rays, because gamma rays are even a little more powerful than an X-ray. And so you can get some of these reactions within the body, right? So dose can go up. So that's photoelectric. The next one is called coherent. Sometimes it's called Rayleigh. And this is kind of your typical scatter that you talk about in X-ray, but essentially you have an incoming photon that travels very close to the nucleus. It gets attracted, but doesn't actually hit anything, and it just makes it turn and curve and go off somewhere else, right? So it's just deflecting off, again, providing scatter radiation, increasing patient dose. This can happen with gamma rays as well. And then Compton scatter is the other one that you've probably heard of. This is where your gamma ray comes in and strikes an outer shell electron. That electron is kicked out. We call that a Compton electron. So that electron can go cause problems. But then the incident photon, instead of being absorbed here, it's scattered off and shot off in another direction. So again, patient dose increased here. And then this last one I'm only mentioning because it's in your book, and it also, the board mentions pair production. I don't want you to confuse this with beta plus. This is not beta plus, okay? So in beta plus, you have too many protons and it's the nucleus doing something. In pair production, this would be an incident photon coming into the nucleus with such great power that what it does is it kicks an electron off and it kicks a positron off, the positron, a positive electron that we talked about before. Okay, when that happens, this electron goes flying off to wherever, and what happens with the positive electron or the positron is you have that annihilation reaction. It finds the free electron, creates the reaction. The reason why I think it's funny that they include this is that you have to have a strong enough incoming photon to kick that off, somewhere in the up in the neighborhood of 1 mega electron volt. And the problem is no X-ray machine produces that, and you're not going to get that really from any of the gamma stuff either. That's why we can use it in beta plus, because it's happening within the nucleus, is deciding to do that itself, right? But in this case, that's what it is. I'm sure there are some powerful situations. I don't know if it's like a nuclear power plant. I have no idea. But that's what pair production is. Don't confuse it with beta plus, which again, beta plus is happening because the nucleus is decaying. This is happening because something came in with enough force to kick off an electron and a positron and then have that annihilation reaction. Okay. All right. So that is it on the physics, you guys. You made it. And I know your brains are probably fried. I remember when I was in your position, my brain was quite fried at this point. You'll get this stuff. You'll hear it enough that you'll get it. Go back and study it. Go back and look at it. And even just talking amongst yourselves, it will come eventually. We have probably about 20 minutes left of our class. I'd like to go through the radioactive decay equation and look at some things. I guess the question I would have from you is, you want to give me some thumbs up on who's looked at this? Who's watched my video? Maybe we'll go, maybe put it in the chat. Get some thumbs up in the chat. Okay, I'm seeing a few thumbs ups here and there. So I think what I'll do is, I think I'm going to still go through the decay equation. And then maybe I'll turn on, I have an iPad that I can actually do some problems on. I'll turn on the iPad and maybe we'll go through it. If there's anybody that's, as we do this, that's starting to get really lost, just tell me, interrupt me. I'll stop and go back to some of the basic principles. But what I think I'll try to do is maybe even grab a couple of things from your homework and kind of try to answer some of those math questions. But hopefully you've watched my other video. I just basically took an old lecture and snipped out that part and put it in there. I found over time that it's helpful for you to hear it once before I say it again. So I'll try to cover as much as I can. Again, it's probably going to go a little past our time, and just I respect your time, so do whatever you need to do. Okay. So on this first part, I'm just going to bust through this quick. Again, algebra is what we use in nuclear medicine, so that's a plus because we don't have to get anything too advanced. You need to know how to work with fractions, add, subtract, multiply, and divide, be able to do algebraic fractions to do nuclear medicine stuff. Understanding exponents is important, and understanding how to convert from one place to another, and understand, again, really quick right here, if I have 3.7 times 10 to the negative third, all that means is I started where my decimal was in 3.7, and on negatives we go to the left 1, 2, 3 decimals and you get 0.0037. That's what 3.7 times 10 to the negative third represents. And then here we got 37,000, and all we did to get there is we started where our decimal would be here, and it's 10 to the fourth, so 1, 2, 3, 4, we got 37,000. And then remember that 10 to the 1 is just 10, and 10 to the 0 is 1. And so that should get you through that. I'm going to, identify these 3 important ones. Again, these are important. These are prefixes. Understand that when we say 10 to the 6th, that's 1 millionth. So it's small. It's a millionth size smaller. Again, and that's micro. You're going to work with microcuries, right? You're also going to work with millicuries. So understand that's 10 to the negative third, so that's 1,000th. So again, realize that if you're going from milli to micro, there's 3 decimal places. Why? Because we went from -3 to -6. So if you're changing from milli to micro or back and forth, there's 3 decimal places that you're going to move that decimal, okay? The other one that you'll see is giga. Remember that giga represents 9 billion, okay? 9 billion. I'm going to skip this and go straight to radioactive decay because of our time. But again, I cover this in the other video, so go look at that video. And if there's more questions, we can hit this at another time as well. I'm fine with doing that. Or if you guys have questions or you're feeling like, oh man, I don't get this, and a lot of you are texting me and messaging me that, then we can pop on and do another quick, in an evening sometime coming up, we can pop on and be like, hey, let's go over this and let's answer questions. Okay, so because I have that video on Canvas, I'm going to skip that. And I'm going to skip the Curie to Becquerel conversions. On the video, I had a lot more information on the slides. On your current slides, I tried to distill the information into more of just the important things to know. So again, I'll let you watch the video for those. Let's come back to that if we need to. I want to get to the most important thing, which is the decay formula, okay? In our 20 minutes that we have left. Okay, so I mentioned this in my video, I'll mention again. When I first learned this, I was like, what in the world is this? This looks like a totally different language. At the time that I had taken it, I hadn't done math for quite a few years. And I looked at this and was like, this is overwhelming. I have no idea what to do. So as I say in the video, you need to just trust me. I'm going to teach you what the parts of this equation are first. Then I'm going to distill it into the equation that I want you to memorize and use. We're going to identify what each of the parts mean, and then we're going to look at some problems and just say, here's how to take what's in the problem, plug it in the right places, and then here's how to do the math. Even if you're not up on math, I will show you the steps and help you get through it. Trust me when I say that you're going to do enough of these over the course of the program that you'll get this just by sheer doing that, okay? So to start out, the radioactive decay formula, this is how we figure out radioactive decay over time. And I'll start saying these and then I'll identify them and you'll get it later, but this stands for activity equals original activity times by the log of negative lambda times time. Now again, I probably just spoke a different language, so let me go back. So original activity is the activity that you had when it was the greatest. So if you're saying I've got 10 millicuries, what will it be in 4 hours? Right, your original activity is that 10 millicuries, and your activity is when it got small, when it decayed away. Okay, so that's why you have this O. The O has nothing to do with anything you're doing for the algebra. It's just a subscript to identify original activity goes on the right side of the equation, activity goes on the left. Okay, then it's times by a log. So what the heck is a log, right? So all a log represents is exponential growth or decay. So anything that happens exponentially. So the example that's easiest to use because we're all in healthcare is if somebody has some kind of bug or some kind of sickness, and then they get 5 people sick, and then those 5 people get 5 people, each time that steps up, you don't just have a doubling, you have an exponential growth. It's bigger and bigger and bigger each time, right? Well, in radioactive decay, we're working the other way, we're going smaller. So every hour that passes by, our radioactive activity gets smaller and smaller and smaller, and it's exponentially smaller. Because when part of it's gone, then it makes the next group of decay even smaller and smaller and smaller, okay? So that's the reason why we have the logarithm in there, okay? Now, it's a negative. That negative part of it up here is because we're working with radioactive decay, right? So it's not going to be a positive log. It's going to be a negative log every time. Now, lambda. What the heck is lambda? Lambda, I've written over here, it represents decay constant. And what that is in our case is it's the number 0.693 divided by the half-life of whatever nuclide we're looking at, okay? So that's what lambda represents. 0.693 is what we call decay constant. It's what we call Euler's number, and it was created by a scientist. Last name was Euler. He came up with a mathematical formula or a number of being able to represent something that constantly changes exponentially, okay? So don't worry about that. You're never going to be tested on anything like that. All you need to know is memorize this number, okay? 0.693, 0.693, 0.693 over half-life. That's what lambda is. And then time is just the time of decay that you had. So if I said I had 10 millicuries and 4 hours later I have how much, then that's the 4 hours, right? So that would go in the time. So now that I've kind of defined the equation itself, here's the one that you'll memorize and write out, right? Instead of using lambda, we just insert that 0.693. So you have activity equals original activity times by the log of negative 0.693 times time all over the half-life, okay? And again, negative because we're doing decay. When we use this formula, there's the parts of this formula we can solve for and that you'll be asked to solve for are activity, original activity, time, and half-life. On your calculator, you need to find these functions on your calculator because anytime that we're trying to solve for activity or original activity, part of this equation, we're going to use this e to the x logarithm function. Sometimes on some calculators, this is just an e. It's not e to the x. You'll have to find that on your calculator. The other one that we'll use if we're solving for time or half-life is this natural log function or ln function, okay? So this is how we do it. So now let's try to take a look at some examples and see how we do it, okay? And maybe I'll just kind of go through these examples until we get as far as we can, and then we'll pull out the iPad. This is the same example I have on the video, so we'll buzz through it just in case any of you, we'll just cover it. It's good to hear again. So in this, before I start all this, I want you to pay attention to the notes I have over here. These are really important. These are tips to help you because even when you get to your boards and you're like, oh, I know the equation now. If you don't be systematic about it, you're likely to make stupid mistakes. Even though you know the stuff, you'll make a dumb mistake, right? It's easy to do. So we want to get it right the first time. That's not really a tip. It's just a reminder of why there's all these other tips. AART uses a Windows calculator, so you might want to become familiar with where the buttons are on a Windows calculator. I think it's very similar to probably an iPhone calculator, which is what I use most of the time. I would recommend always writing down your formula. When you get into your boards, write it down. You have it there. You don't need to think about it anymore. Days of memorization are done if you just do it right when you get in there. So write down your formula, which is what I did here. Then you're going to write down your quantities after reading through. So I often would do mine like this when I was going through boards. I'd be like activity, original activity, time, and half-life. And then I would fill it in based on what I was reading. So fill in what you know, calculate for what you don't know. And then at the end, always ask yourself, the answer I get, does it make sense? With radioactive decay, it's nice because we can always think like, okay, if I've got this certain amount and I'm wanting to know what it is later, I've got to get a smaller amount. Or if it's asking me that in reverse and it's saying, I have this amount, what was it along, what did it used to be 4 hours ago? Well, then I know it's going to be bigger then because it decayed down. You just have to ask yourself those logical questions, okay? So in this one, super simple. You measure technetium-99 dose at 10 millicuries. What will the dose measure in 2 hours, okay? Wrote down the formula. Let's fill in our thing. So you measure technetium dose at 10 millicuries, and it wants to know what it's going to be in the future. So what's our original dose? Our original activity is 10, right? Because it's going to be something else later, and that will be the activity later. And that's when it's asking us. So 10 goes in our original activity. We don't know what the activity is. That's the question, is what will it be in 2 hours? We now know 2 hours is our time that's passed by, so we can put that in. And then because we're working with tech, we know that tech has a 6-hour half-life. Now, I didn't write that in here. You guys should know that just right away. Technetium has a 6-hour half-life. On other ones that I've asked you to do, I've put the half-life in, but honestly, by the end of your program, you're going to know the half-life of a lot of the common ones you use, and probably in your boards, you'll, by that time, know what the half-lives are. So don't stress too much about that. All right, so now that we have our defined terms, and we know what everything is, we're going to plug it in. So activity, which we don't know, equals 10 millicuries times by the log of negative 0.693 times the 2 hours, which I wrote here, and then all over half-life, which is 6 hours, which I wrote here. You'll notice that I then crossed off the hours. Try not to get in the habit of skipping if it's hours or not, because it could say that it had been minutes, but you know that tech is a 6-hour half-life. You'd have to convert tech into minutes, right? So make sure those need to be the same in order to work this equation. They got to both be hours or both be minutes or whatever the time is that they're asking. So you'd have to convert if that was the case. In this case, they were the same, so I got rid of them. When what we can do now is we look at the equation and where can we do something. In this case, if you have all of your variables up here after the log, then you can work this part of the equation. If you don't have all of your variables, you have to do something else first. In this case, we have all the variables. So when I do negative 0.693 times 2 hours divided by 6 hours, I get negative 0.231. Okay, so now my equation reads A equals 10 millicuries times E, or times the log of negative 0.231. Okay, now to get out of this logarithm form now, we're going to have to find this e to the x on our calculator. You're going to put negative 0.231 into your calculator. You're going to hit the e to the x button, and it's going to give you another number. In this case, my calculator gave me 0.794. When you do that e to the x, it gets rid of this logarithm. So now you have an equation that is no longer in a logarithm form. You have A equals 10 millicuries times 0.794. When you do the math on that and times it by 10, you get A equals 7.9 millicuries. Now, you ask, does it make sense? Is it logical, right? You started with 10. We know that the half-life is every 6 hours. So in 6 hours, it would be down to 5. We were 2 hours, so it's not 6. So we're somewhere in between. We should be between 10 and 5. And look, we are. We're at 7.9. So is that logical? Yeah, it's logical and it's reasonable. Okay. On the next one, I had put in here, and I'll let you guys go and watch this. But in this case, I said you measure a dose at 10 millicuries. What was the dose measuring 30 minutes ago? So this is a trick because now you got to realize that your original activity was what it was 30 minutes ago, because you're not looking into the future, you're looking into the past. So now you got to say, okay, well, my original activity is the thing I'm missing. I don't know what it was 30 minutes ago, but I do know what it is right now, which is 10 millicuries, and it's asking me what was it in the past. So I'm going to put my 10 millicuries here. Now I tricked you guys on purpose on this one, and I put 30 minutes because tech, you have to use a 6-hour half-life, and it's 30 minutes, right? You can't have minutes and hours and have this equation work, so you have to convert it. What I chose to do when I went down here is I have my 6-hour half-life, and then I converted minutes into hours, which would be 0.5 hours or a half an hour, right? You could also go the other way, and you could say, I'm going to leave it at 30 minutes, but then you've got to convert 6 hours into minutes, right? So then you'd have 60 times 6, which would be 3,600 minutes. And then you could keep the 30 minutes on top. That felt harder to me than just putting 0.5 hours and 6 hours, okay? And then once you're at this point, now we can go ahead and solve. Again, if we don't have a variable over here, which we don't, we can go ahead and solve by using e to the x. I did the math here, got this number in my calculator, put that negative number in the calculator and hit e to the x and got this number. And so now I'm down to 10 millicuries equals the original activity times 0.9439. When I do the math on that, what I did is I said, well, I need to get activity by itself. It's being multiplied by this number. So what breaks apart multiplication? Division. So I'm going to divide this side by 0.9436, and I'm going to divide this side by 0.9439, not 6, 9. So now I have 10 millicuries divided by this equals the original activity. When I did that division problem, I got 10.6 millicuries. Now, does it make sense, right? 6-hour half-life, it wants to know what it was 30 minutes earlier. So we're only minutes. Remember, 6 hours would be half, right? And so if you think about, draw that out, it makes sense that it's only slightly bigger because it hasn't been very much decay time. It's only been 30 minutes. So it makes sense that we got rid of only 0.6. Because if it would have been 6 hours, we'd be down to 5, but it's only been 30 minutes, right? So if it would have been 6 hours, it would have been double, so it would have been up and greater amount, but we're 0.6. It would have been 15. Sorry, I probably just confused the heck out of you. But we're down to 5.6, and that does make sense. Okay, so then in these next ones, we're going to answer the question of half-life and time. And in this case, we're going to switch, and we're not going to use that e to the x function. We're going to use the ln function on our computer, or on our calculator. Sorry. So in this example, a dose of tech is originally measured 100 millicuries. Now it measures 9. How much time has elapsed from the original measurement? Again, I put in those in. So it gave me my activity and my original activity. What it didn't give me is the time, and I know I have text, so I still have 6 hours. So notice I plugged everything into my equation, and what you notice is I have a variable over here, right? I can't solve this part of the equation with a variable in it. You've got to do something different. So in this case, since we can't do anything with the logarithm side, what can we do over here? Well, this logarithm is being times or multiplied by 100 millicuries. So we can get rid of the 100 millicuries. Because it's being multiplied, we divide. So what I did is I divide both sides of the equation by the 100, which over here I've got 9 millicuries divided by 100 now equals the log of, on the right side, that 100 canceled out. So I have the log of 0.693 times time over 6 hours. Okay, so that's what I have. Now, you might be tempted to come and just do this division, like 9 divided by 100 and get a decimal. The reason you don't want to do that is a couple of rules of algebra come into play right here. The first thing is that eventually we're going to want to get out of algorithm, okay? We can't get rid of, we need to be able to use our ln function. We can't use our ln function with negative numbers. Your e to the x can be used with negative numbers, but your ln function can't. So one problem we have over here is there's a negative. So I can't just start using, get it out of the exponential form. So that's one of our problems. We've got to get rid of that negative. So first we're going to do that. And that's why I didn't get rid of this equation here, this 9 divided by 100, because we've got to get rid of that negative eventually. And I know that in advance. So in algebra, one of the principles, if you all remember back to those days, and maybe for some of you it wasn't that long ago, but you can get rid of the negative on one side of your equation by flipping the fraction on the other side of the equation. Okay, so that's what we're going to do to get rid of that negative. So we flip the left side of the equation, and now it's 100 divided by 9, and it makes it so that the right side of the equation, now the negative becomes a positive. Okay, so that gives us a positive exponent value. And so now, in that state, we're ready to use our ln function. Okay, we couldn't use it with the negative. So now what we can do is we can come over and do this division. So we'll come onto the left and we'll do 100 divided by 9. When I did that in my calculator, I got 11.11. So now my equation reads 11.11 equals the log of positive 0.693 times time over half-life for 6 hours. This is the stage now where we're ready to use that ln button, okay? And we're going to use that ln button on the left side of the equation because it's like a reverse of the e to the x, right? It's a reverse of the log. So it gets rid of logs, but you have to do it on the other side. So we're going to take that 11.11 and we're going to hit this ln button. So put that into your calculator, hit ln. When you do that, you're going to get 2.408, okay? So now my equation, I replace that. I'll put 2.408 equals, and now remember, when we use that ln function, we got rid of the log. So our e disappears, and now we just have 0.693 times time over 6 hours. Now, I didn't finish out just the algebra here. There might be a few of you that haven't done algebra while they're cursing me, so let me just let me just talk you through it. You should be able to solve this. Is just basic algebra. But on this, if I were to solve this equation, I would recognize I got to get this t by itself. So the first thing I'm going to do is it's all being divided by 6 hours. So the opposite of division is multiply. So if I multiply this side of the equation by 6 hours, it will get rid of the 6 hours. But if I do that on the right, I have to do it on the left. So I would multiply the left by the equation. And then I would just have, in fact, we can quickly do it. So we'll go 2.408 times 6 gets 14.448 is what I got on mine. And then you just have to do the basic division of dividing by 0.63 to get t by itself. Anyway, if you don't understand that, let me know. It's simple algebra. We can go over it, and we can also go over it. Kyler, I'll answer your question in 1 second. But I ended up getting t equals 20 times, or 20.8 hours is what I got. Okay, is that logical? We went from 100 millicuries down to 9 millicuries, and we have a 6 hour half-life. So every 6 hours it goes in half. And we start out with 100 millicuries, so that's logical that we'd be smaller. Now, Kyler asked, can you explain why you flipped the 9 over 100? Yes, I'll go back. So I mentioned that to use the ln function, we can't have a negative in this logarithm exponent value, okay? We need to be able to use that ln. We can't do that with a negative. So the way that in algebra, the algebraic principle is that you can get rid of a negative on one side of an equation by flipping the other side of the equation. So all I did was I took this 9 over 100 and I changed it to 100 over 9, and that made my negative turn into a positive on the right side. Okay? And so then with the positive on the right side, I then divided 100 by 9 and got this number, and now I'm ready to use my ln function on this number here, which gets rid of the logarithm and changes it into something without a logarithm that's basic algebra. Did that help, Kyler? That makes sense. Thank you. Okay, good. Perfect. Perfect. We're out of time, so we're ending. I want to pull up my iPad and show one other thing. So this is the same way you would use, guys, remember, to solve time or half-life. So for your half-life down here was the thing that had an unknown. You would still have to do the flipping and get rid of the negative and use the ln function and then solve basic algebra. It works exactly the same. Okay, so just remember, ln, I'll go back to this. ln function is going to be used when you're trying to figure out time and half-life. And e to the x is going to be used when you're figuring out activity and original activity. Okay, so again, I'm going to pull out my iPad and do one more at least, and then answer any questions. Again, if any of you need to leave, we're officially out of time, so you're welcome to do that. I'm going to grab my iPad. And let me give my... So I'm going to stop sharing the slide. And then got myself logged in as a different login. Probably use from my iPad. So hang tight 1 second. Okay, do you guys see? Let's see. Do you guys see the whiteboard? Okay.
Yep. All right. Okay. So what I want to do is I wanted to cover one more kind of principle. It's something you run into on your homework. So we're going to ask this question here. I'll try to write it on the board here. So we'll say, what percentage is left of 10 millicuries of tech for 10 hours? Okay. Sorry about my crappy writing on this iPad. Okay, so how would you solve this? Because again, you don't have activity, right? You don't have activity and you don't have original activity. So what are we going to use to solve this? And this can throw people off because you can get percentage questions on the boards, and I put one on mine just for that very reason. What I want you to think about is, if we're asking for a percentage of something, then what's the original activity, original amount of that in terms of a percentage? Who has a guess?
100.
Yeah, exactly. any percentage of something in its original place is 100. That's exactly right. So if we're asking what percentage is left of something after 10 hours, then we know that our original activity is going to be 100, right? And that means, what's that?
Can you write more in the middle of the screen, like to your right? We can't see anything behind all of your little tools
Oh,
of what you're writing. Awesome, thank you.
I can move it, and then let me put my iPad sideways because now I'm off screen. Whoa, now we're getting real crazy. Can you see it now?
Yes.
Okay, I'm gonna go a little bit. Tell me if that goes away again. Okay. All right, so our original activity would be 100, right? And that means our activity that we're looking for, or our activity is that unknown, right? It's the percentage that we don't know. Okay. And then we know that, did I get rid of, oh, I got rid of 10 hours. We know that our time is saying is the 10 hours, and our half-life we know because its tech is 6. So now we can plug that in. I am gonna move the screen up so we have room to work. Okay. So if I plug all that in, I'm gonna say activity equals original activity times by the log -0.693 times time. We know our time is 10 hours. All over our half-life. Okay, so now I can solve that logarithm portion because again, there's no variable. So I'm gonna throw that in my calculator. Any of you that want to do this with me can. In fact, does someone want to be our calculator person? Let's do that. So let's have you guys tell me the numbers and I'll just write them. Give me a volunteer. Somebody be brave.
I can do it.
You can do it. All right. Who was that?
It's Madeja.
Deja, you're awesome. All right. So what I want you to do, Deja, is you're going to put -0.693 times 10.
Negative 6.93.
And then divide that by 6.
Negative 1.155.
Okay. Not my pen. Okay, so then we still have a log of negative what?
1.155.
Gosh, come on, right. And there we go, 155. Okay. And that's still going to be times by 100. We're just going to have our activity. Okay. Let me know if I'm putting things too far on the screen. At least the equation. Okay. All right. So now we can solve this. Again, we have our e to the x function that we're going to use on our calculator. That's the next thing we're going to do here. So do you know where your e to the x function is?
Yeah, it's 0.315.
Okay, sure did. So for everybody that, just in case you didn't catch it, what she did is she put negative 1.155 in the calculator and hit the e to the x function and then give it to me again.
0.315.
I'm going to interrupt real quick. Can you remind me how you got 100, please?
Yes, so 100 was 100%. So that's what I asked at the beginning. I said, if we're going to talk in percentages and we need to know an original activity, well, if we're wanting a percent of something, then the original of that thing would have always been 100, right? Because we're asking for an amount in percentage, like what is the percentage after 10 hours? Well, then the original percentage must be 100 because you're going to ask for a percentage of what it is later on. Did that make sense?
Yes, thank you.
That's where we got the 100. That's 100%. And maybe what I should do is percent. That will help. Okay, so now we're down to a super simple, right? So, okay, I'm going to have you times 0.315 times 100 is all we have left to do on that, right? So
31.
Yep, that's pretty easy. Probably do that without the calculator, right?
Something like that.
31.5, and it's in percentage, right? So 31. So we go from 100%, and then 10 hours later, we had one half-life pass by. One half-life would bring us down to 50%, but we had a little more than a half-life pass by because it was 10 hours, right? So it makes sense that it would be less than 50 and somewhere between 0 and 50, right? 31.5%. So I wanted to show you that because there's, I think, one or two of those on homework. But again, when you're thinking in percentages, just think, okay, 100% is always going to be your original activity, always. Any questions on that? All right. I'm going to take back. Find my tape back here. All right. Okay, let me go. That was all I was going to cover today. Does anybody have any questions on anything we covered?
On the last slide on the PowerPoint, I got majority of the way done, but I'm a little confused at like the second to last step, and I was wondering if you could kind of just go through that
On the
one.
very last slide? Okay.
Yeah, because I got to the 31.25 equals e raised to the, but I don't know why my brain's not
Okay.
doing its job.
Let me show the slide real fast and do that really quick. Oh, man, sorry. I got to go back and take myself back from my.
Sorry.
Oh, you're good. It's not your deal. I'm just forget that I have to do that sometimes. Why does it look like me? For some reason it's not letting me take. I gave host to the whiteboard on my iPad. Now it won't take it back. Shoot. Let me see if I can close out iPad. Let me see. Maybe I can do it on the iPad and give myself back permission if that's easiest. There we go. Okay, sorry about that. The joys of doing this on technology from afar. Bye. Okay, you should see my slide again. You see it?
Yes.
It's the right one.
Yes.
Okay, and you said you were down here on this step of 31.25.
Yes, but I think I might have figured it out, but can you still go over it?
Yeah. Okay, so we'll bust through this one real quick. I'm just gonna start from the top, and so that people can walk through it and they're not just jumping in the middle. But a nuclide has an activity of 20 millicuries. 40 days later, the activity is 640 microcuries. What nuclide is? This has a couple of things to screw you up in it. First of all, we're asking what nuclide it is, which means we don't know the half-life because we don't know the nuclide. So the half-life is what we're looking for, right? So that's your first clue. The other thing to pay attention to in here is that you've got it in microcuries, and your original activity is in millicuries. So you've got to convert one of those two. Easiest, in my opinion, and I put that in parentheses here, is you convert 640 mics to 640 millicuries. Okay. Remember, from mic to milli is 3 decimal places, so you start right here and go 1, 2, 3. You're going to be there. So that's how you get your 0.64 millicuries. So when we write all that in, we're going to do our activity is 640 microcuries, and that's the activity that we currently have because we're talking about 40 days later. The original activity was, or excuse me, sorry, I said that backwards. The activity is 640 mics. The original activity was 20 millicuries, right? because we want to know what it would be. Or gosh, sorry, my brain. We get to the 640 mics because we've already waited. We want to know what nuclide it is. And so we have that difference. I'm sorry. Brain's fried. So 640 to 20. Then our time we know is 40 days. And then again, what we don't know is our half-life because it's asking us what element, what nuclide we have. Okay. So when we plug that all in, our 640 mics equals 20 millicuries times by the log of 0.69, negative 0.693 times 40 days over half-life. Again, I chose to change get everything both in millicuries, so it'd be 0.64 millicuries equals 20 millicuries times the log of negative 0.693 times 40 days over half-life. Okay. Again, what we need to do here is we've got a variable on the right, so we can't really do anything with the logarithm at present. So we need to get rid of this 20. The only thing we can do is get rid of the 20 millicuries, and it's being multiplied. So we're going to divide it by 20. So if we divide 20 on this side, we get rid of 20. If we divide 20 over here, we get the fraction 0.64 times 20, or divide by 20, sorry. And that's equal to the log of, again, 0.693, 40 days half-life. Okay, so there's where we are there. Now, again, remember, we can't use the ln function, which we have to use when we're solving for half-life or time. We can't use that when there's a negative. The only way to get rid of the negative is we can flip the left side of the equation, and that'll get rid of the negative on the right. So that's what I did here. I inverted. I've got 20 divided by 0.64 equals the positive now logarithm of 0.693 times 40 days all over half-life. Okay, so here we are at that. Now, I do the division here to get a normal number to use with my ln function. So 20 divided by 0.64, I got 31.25 equals, again, the rest of the equation. This is where now I can use the ln function on that 31.25. When I did that in my calculator, I got 3.44. Okay, so I put my 3.44 now equals 0.693 times 40 days all over half-life. And again, I probably should add these on here, but again, this is a basic equation now that you would solve. If you're going to solve this at this point, you need to get half-life. You need to get rid of that denominator. So this is being divided by t1/2, this side. So if we want to get rid of that, we got to multiply this side by t1/2. T1/2 cancels on both sides. And then we have multiplied on this side, and we get t1/2 times 3.44, and then we solve from there. If you want, we can pull up the iPad and do it really fast. We get the iPad back on. Do you want to do that? Yes? Okay. I probably should have figured those out. I just kind of left it with the algebra, but I shouldn't, because you're probably just like me, and back in the day, I needed a huge refresher on algebra too, but that's okay. Let me, I wonder if I just make myself co-host, if it will let me do board. Okay. Yep, we will. Okay. You guys see the whiteboard again?
Yes.
Okay. This is the middle of my whiteboard. Is that good enough for you?
Yes.
Okay. All right. So I'm going down to that very last step, and what we have is 3.44. And that is going to be equal to 0.693 times the 40 days all over our unknown, which is our half-life. Okay, so I need to get rid of that denominator. That's the first step I'm going to have algebraically. So to get rid of that, I'm going to multiply both sides because it's being divided. So over here, I'll multiply this by t1/2. Okay, and when I do that, I cancel these two out. And then I'm going to multiply the other side by t1/2 as well. Okay, can you guys still see that? Okay, so then what I get is I get 3.444 times t1/2 equal to 0.693 times 40. Okay, we all good up to there?
Okay, so then on the right side, I can obviously combine those two. So I'll do 0.693 on the calculator times 40. And I get 27.72. And over here, we still have 3.44 times t1/2. So that's supposed to be a multiply there. Okay. And now we're going to have to get t1/2 by itself because that's what we're trying to solve, obviously. So it's being multiplied by 3.14, so we need to divide it. So if we divide this side by 3.44, we get a cancellation there. And if we divide this side by 3.44, it's a really bad 4, it looks like a 6. So I'll put that in my calculator, 27.72 divided by 3.44 equals 8.058. And I'll just leave it at 8.05 for now. And then that, all I have left on the other side is t1/2. So the half-life of my nuclide that I'm looking for is 8.05. And remember, we were in days. I should have left days in there. And if you look on charts, that's I-131. That's the half-life of I-131.
Thank you.
That makes sense?
Yes, thank you.
Perfect. Perfect. All right, let me unshare that. And I think we'll end it unless there's any more. Remember that you get your stuff studied, get your tests done, and then move on to studying section 2 and preparing for section 2 so that when we have our next lecture. Okay. All right, I'm going to end it. I got to go to work.
Thank you.
You're welcome, guys. We'll see you next time. Any of you that need anything between now and then, message me.